Hello everyone, I hope you are doing great. My name is Irsa Khan and today I will be presenting my project for parallel and distributed computing. And the subject of my project is parallel versus distributed image processing, a journey towards efficient image processing. So let's begin. For the better understanding of this project, first we will have to learn about Kubernetes architecture. So in this section, we will explore the fundamental architecture of Kubernetes, that is a powerful container orchestration platform. We will dive into the key components and their roles within the Kubernetes ecosystem, providing you with a clear understanding of how Kubernetes manages and orchestrates the containerized applications. By the end of this presentation, you will have a solid grasp of Kubernetes architecture, empowering you to effectively deploy, scale, and manage your containerized workloads. So first of all, let us see what is Kubernetes. Kubernetes is an open source container management tool which automates container deployment, container descaling, and container load balancing. Here we have some of the features of Kubernetes that we will discuss in detail. So some of them are automatic bin packing, service discovery and load balancing, storage orchestration, self-healing, secret configuration and management, batch execution, horizontal scaling, and automatic rollbacks and rollouts. So first of all, let's dive into the main components of Kubernetes architectures. We have master nodes, worker nodes, and distributed key value stores, that is etcd. So let's see what we have inside the master node and how it works. So master node is responsible for managing the Kubernetes cluster. It is the entry point for all the administrative tasks. Can be more than one master node in the cluster, but only one of them will be the leader. Kubernetes uses etcd, and I will be explaining etcd in further detail. The components of Masternode includes API server, scheduler, controller manager, and etcd. So first of all, we have controller manager. The controller manager is a key component that runs various controllers in Kubernetes. Each controller is responsible for maintaining the desired state of different aspects of the cluster. For example, the node controller manages the status of nodes. The replication controller ensures the desired number of pods and replicas, and the namespace controller handles the namespace related operations. Next, we have API server. The API server acts as a central management point for the Kubernetes cluster. It exposes the Kubernetes API, which allows users and other components to interact with the cluster. The API server handles incoming requests, validates them, and processes operations such as deploying pods, scaling applications, or updating configurations. Then we have our scheduler. The scheduler is responsible for assigning pods to worker nodes based on resource availability and workload constraints. It evaluates the factors like CPU and memory requirements, node conditions, and various policies to determine the optimal node for pod replacement. The scheduler ensures efficient resource utilization and load balancing across the cluster. And finally, we have key value store or etcd. So etcd is a distributed key value store that acts as a cluster's persistent database. It stores the configuration data and state information of entire Kubernetes cluster. etcd ensures consistency, reliability, and fault tolerance by employing a distributed consensus algorithm. It is accessed by other master components such as API server and controller manager to read and write cluster information. So next we have worker node, and here is the brief structure of worker node. Let me explain the components of the worker nodes. So in the Kubernetes worker node, two important components are pods and kubelets. So pods are the basic execution units in Kubernetes. They represent a logical group of one or more containers that are deployed together on a worker node. Containers within a pod share the same network namespace, IP address, and storage volumes, allowing them to communicate and collaborate closely. Pods are designed in such a way that they can be easily created, scaled, or terminated. Next, we have kubelet. So the kubelet is essential agent that runs on each worker node in the Kubernetes cluster. It acts as a primary point of contact between the Kubernetes master and the worker node. The kubelet is responsible for managing and maintaining the state of pods running on its node. It ensures that the desired number of pods is running, monitors their health, and takes necessary actions to maintain the desired state. Then we have our kube proxy. So kube proxy operates at the network layer and performs two basic functions. The first one is service proxy. Kube proxy maintains network rules and configurations to enable transparent access to the services running within the cluster. It ensures that the requests to services are properly routed to the correct destination pod, regardless of the pod's location or any potential changes in the cluster's topology. The kube proxy achieves this by setting up and managing virtual IP addresses, VIPs, and routing rules for service endpoints. Then we have load balancing within the kube proxy. So kube proxy provides load balancing for services that have multiple pod replicas. It distributes incoming traffic across the available pods for a given service, ensuring optimal resource utilization and high availability. By spreading the load across multiple pods, kube proxy helps prevent any single pod from becoming overwhelmed and provides fault tolerance in case of any pod failures. And then we have state management with etcd. So what it does is etcd in Kubernetes involve utilizing etcd as the distributed key value store to store and manage the cluster's configuration data, state information, and metadata. So some of the brief components of state management with etcd are consistent data store, cluster-wide configuration, metadata storage, watch API, and high availability and fault tolerance. So lastly, we will see how the communication between the external world and the pods is carried out. So it has our container deployment pipeline. So first of all, you build a service using Docker, and then you deploy or compose it to Docker Hub, and then finally you deploy your application with all its dependencies to the Kubernetes. So this is how all our Kubernetes work is done. Now let's see how I build my image processing project using Kubernetes. So first of all, we have the overview of the problem: processing large dataset, computational complexity, storage and memory constraints, scalability, and efficiency. These are the certain problems we usually face while processing the large datasets. So my project aims to resolve these problems. We have already discussed the Kubernetes and Docker integration. So here we have overview of Kubernetes that I have already discussed in detail. Then setting up Kubernetes environment with Docker. Here are few commands that are easily available on internet that you can use for setting up Kubernetes environment on your system. Then here are the screenshots of what I did and how I configured my Docker and Kubernetes on my local system. This is done on my local machine using Linux Mint. And then inside my Python script, I did separate parts for parallel image processing and distributed image processing. So in parallel image processing, I used dividing a task into smaller subtasks and executing them concurrently on multiple processing units. So here is a code snippet for parallel image processing, and here we have a code snippet for distributed image processing that will run on multiple nodes using Kubernetes. Then here I have compared the results of parallel versus distributed image processing. First of all, I did a small dataset feed, and it took 3.08 seconds for parallel processing and 0.04 seconds for multiple or distributed processing. Then I feeded a large dataset, and it took 30.15 seconds for parallel processing and 0.04 seconds for distributed processing. And then I feed massive dataset of over 30,000 images, and which took me 30.15 seconds for parallel processing and 0.04 seconds, only 0.04 seconds for distributed image processing. So here is the clear difference between parallel and distributed datasets. Then let me give you the demo of my project. So I made this input directory and output directory for this script. So input directory has this data set of huge data set of images. We have here over 30,000 images by now. Previously it was 25,000 images, as you can see. And then we have our output directory, which is empty for now. After running the script, we will see the output in our output directory. Here is my Python script. It uses OpenCV library of Python to process the images, and then it saves the images into the output directory. So we have our parallel processing code and distributed processing code. Let us run the script and see the difference between parallel image distribution and distributed image processing. Now it will process all the images in our dataset of 30,000 images one by one, and then we will compare the parallel versus distributed time. So here is the result. It took 58.08 seconds for parallel processing and only 0.05 seconds for distributed image processing. So there is a huge difference between both of them. And now we will see our output directory, which has all the post processed images. So this was my small project for parallel and distributed computing. I hope you like it. Thank you so much for your time.